This is the last topic we're going to cover in derivatives. And this is a bit more of an advanced topic. It's not going to show up in the assignments, and it's unlikely that any of you will have a problem large enough that it would matter for your project. But I share it here just it's a good topic to be aware of. As you progress in optimization, it's just good to know that this is out there because it may be useful to you at some point. So again, you don't need to worry too much about this. Is mostly informational here. So this is about sparse Jacobians, and just to motivate, let's remember what happens in let's say in finite difference in complex step and forward mode AD. We need to evaluate this function nx times, right, to populate this Jacobian. So if I had, let's say, I have some function f of x, and I want to compute the Jacobian df dx, right? That's a matrix, and to do that, I have to, let's say here's x, it's x1, x2, all the way to x and x. What I do is that let's just do the finite difference because that's maybe the simplest, but they all work basically the same idea. So I'm going to add some small step to one element, and everything else stays the same, right? And so when I do that, and let's just say we're doing the forward difference, I would get f at x plus h minus f of x divided by h. That's going to give me an estimate for, here's my Jacobian, right? Here's the outputs, F1, F2, all the way to FNF, and then my inputs. All right, so when I did that finite difference, for example, because H occurs only on X2, I'm getting this column of the Jacobian, the derivative with respect to X2. Complex step, of course, works similarly, except for we use an imaginary step, and with AD, we just initialize the dual portion of the vector, right? That we wouldn't add the h, but we'd initialize this dual portion of the vector where everything would be 0 except for a 1 in the place where we want that derivative. And then we'd have to move the 1 around, right? Or we'd have to move the h around. So we'd have to repeat this nx times, right? And reverse mode AD, similar, except for we'd be doing it one row at a time. Okay, so that's just review. But it turns out there are times when we could maybe do this much more efficiently. So here's a motivating example. This is, say, a simplest case. Let's say this is what my Jacobian looked like. Like I knew, I had some information to know that this is what it's going to look like. It's going to be zeros everywhere except for on the diagonal. So in this case, we could actually compute those derivatives for way less cost. So for example, we notice in this case, that means every f, right, like f1, for example, only depends on x1, and f2 only depends on x2. I basically I have n independent functions, more or less. So what I could do, instead of having that vector, x1, x2, x3, x4, x5, where I add h one at a time, I could add the step size to all of them at once, right? And then I could just do this f of x plus h minus f of x over h, and I could get all 5 of these at once because these are independent. So when I add h to this x1, that doesn't affect what happens. That doesn't affect the function value for any of these other outputs. So I can just add h to all of these because each of them are independent. Okay, so again, that's the most simple motivating case. If you had a square diagonal Jacobian, then yeah, we could estimate all the derivatives in one shot. It doesn't matter how big x is, right? Just one forward pass, either forward differencing, AD, whatever it may be. All right, so that's not necessarily super practical. Let's think more generally. Let's say I've got a Jacobian that looks like this. It's non-square. It's sparse. So sparse, this name sparse means that there's lots of zeros. So a dense Jacobian would mean, pretty much every entry has a number. Sparse means I have lots of zeros. There's lots of, so what does that mean physically? That means, like, for example, that my functions like f1 only depends on a few inputs, and every function, or at least most of my functions, only have a few dependencies. There may be many inputs, but the dependencies are sort of they're sparse. So let's consider this more general case, right? Non-square, it's sparse, but there's not like a regular pattern here. So what we're going to look at is what are called structurally orthogonal columns. And structurally orthogonal columns are a subset of these columns that on a given row would have only at most one non-zero between them. So let me just give you an example here. Let's look at, say, column 1 and 3. Those would be structurally orthogonal. So 1 and 3. So if I looked at just 1 and 3, I notice that for each row, right, there's only at most one entry. So there's one here. In this row, there's just this one. In this row, there's just this one. In this, there's none. So in other words, you could think of if I squeeze these together, right, that there would be no overlapping, right, because this would just replace the zeros. So let's say I squeeze them together, the information that's there, I could say there's J11, J23, J31, 0, J53. That would be like combining them together. Whereas if I looked at, say, this row and this row, they're not structurally orthogonal because there's information in these rows. I can't just, flatten them together, if you will. It doesn't have to be just two, right, that are structurally orthogonal. I could have many things. So for example, or many columns. So for example, this column, and this column together are all structurally orthogonal. Again, notice that if I go row by row, there's at most only one entry. So the amount of information per row is only at most one. Okay, so this means I could take this Jacobian and I'm going to smash it down into the minimum amount of information I need. We call this a compressed Jacobian. So let's do that. Here's an example. So there are methods to figure out what we call colors. The colors mean, in essence, how many, what's the minimum number of compressed columns that exist. So for this matrix here, turns out that the number of colors is 3, and there can be, and there is in this case, more than one way to color it, but at the best, there's only going to be 3. I can't have fewer than 3 subsets. So in other words, this is one subset. I said 2, 4, and 5. That's the structurally orthogonal column. So that's one. So how can I group all the rest into these groups? And I want to find the minimum number of these groups. And in this case, it turns out there's 3, and we call this colors. So there's 3 colors to this matrix. And so, for example, these 3, as we just said, are structurally orthogonal. And then we could choose these 2. These are structurally orthogonal. And then I'm left with this one remaining. So I can take that and I can compress it like this. So basically I took these 2 blues, and again, just think of flattening them together. Anywhere there's a 0, there's no information there. I don't care. I'm not computing anything there. I just know that it's always 0. So there's only one piece of information I need to compute per row there. So I could combine these 2. So this is kind of like that diagonal case if you think about those blues, right? Any changes I make to this input here don't only affect this output. They don't affect this output. So I could compute these 2 together in a forward pass. So if I compress these blues together, I compress the reds, and then I have the black, I have these 3 colors. I have now this compressed Jacobian. And so here's the big advantage, is that in this problem here, instead of needing 1, 2, 3, 4, 5, 6 forward passes, I only need 3. And I can compute all the derivatives that I need. Now, I should say this is just small because it's an example. We don't want to write big things, but it's not really a big advantage in this case. This is small, but this comes really into play when my Jacobians are, say hundreds, 100 on one side, or thousands or so, really big ones. Then there can be enormous advantages, right? Like let's say I've got 1,000 by 2,000 matrix or whatever. Instead of having these thousands of operations, it may be that I only have, say, 10 colors in there, and I only need to do 10 sort of forward passes instead of, thousands. This diagonal case here, right? This would work the same. You can see that there's only one color, so I could have compressed this. That's basically what we did, right? I compress it so there's just one column. Okay, and that's why we said we could evaluate this whole thing with just one extra function call. We don't have to do 5. Okay, so you don't. So one wouldn't have to try to figure out these colors on your own. There are coloring algorithms that do this. This is a this field is called, or there's a field called graph coloring, and it's used more broadly than just derivatives. But this is one application of graph coloring. But you can, for a given pattern, it can then determine what are the minimum number of colors that one would need. At least with a heuristic, can determine that. So we talked about these forward passes. So we talked about, or to say, structurally orthogonal columns. That makes sense if we want to think about a forward mode. So finite difference in complex step, forward AD. But if we're using reverse mode AD, we have another option, because remember, reverse mode operates once per function value, once per output rather than input. So in that case, we would look for structurally orthogonal rows. And in this example, it just happens that the number of colors is 3. So this row, for example, is orthogonal to this row. Those are compressed here. Here's one that just left here, and then these two are orthogonal to each other, so those two are compressed here. So again, in this case, instead of 5 reverse passes, we could have reduced it to 3. In fact, AD can be even more flexible now. Imagine this really large Jacobian. We can do forward passes and reverse passes over different portions of the Jacobian, and that can be helpful when we have really large ones where the sparsity structure kind of changes. So we can use kind of this mixed mode. One application where this is pretty common, there are many, but just for an example, is in trajectory optimization. So say I wanted to optimize this path. Let's say I've got this, this is horrible. I'm gonna draw it this way. Let's say I've got, I'll draw a little slower here so I can draw something that looks somewhat okay. Here's my little lousy airplane, right? And I'm trying to figure out some optimal path, right? And let's say I discretize this into a bunch of points, and maybe they're linear, or maybe there's some splines, or whatever they are. I'm figuring out what to do over these little segments of my path, and maybe I'm trying to optimize, say, some control inputs, like what's the RPM I should run my propellers at, or what's the elevator deflection I should use, and or so on, right? I've just got a bunch of design variables I'm going to change. Well, these kind of problems are going to be very sparse because let's say my change in propeller speed or whatever rotation speed is going to affect some local dynamics, but it's going to have no effect way over here because that's my propeller speed over here is independent. So, so I may have these constraints all over the place on the dynamics and inputs, tons of inputs all over the place, but the Jacobian is going to be very sparse because the outputs only depend on sort of these inputs that are localized in time. So that's just a common example where this occurs a lot, where you can have, especially because you may want to have these large trajectories, long in time, lots of discretizations, lots of things you're changing. Even if you're only changing one thing, like just say I'm just changing that speed, I'm changing it independently at every point in time. So that's tons of design variables, but it's going to be very sparse. So these kind of methods can be very advantageous. Okay, so that's it. Like I said, you don't really need to worry about too much for the purpose of the class, but just wanted to kind of throw that in there so it can be in the back of your mind so that you can know that this exists when you need it. That's going to be it for derivatives. When we pick up next week, we're going to start getting into constrained optimization. So now we're going to move from just unconstrained problems and to discuss how we deal with constraints and how that's going to optimize or affect or change our optimality criteria. We'll see you then.